Hey folks, this is Lab 1 for Calculus 1, and we're going to explore limits in this lab. And what I'd like for you to do as we go through these problems, and what I'd like you to do is as we go through these problems, I want you to press pause on the video and explore these on your own. I'll teach you some techniques for doing this as we go along, hopefully using some technology that you have available to you already. For the first problem, we're going to take a one-sided limit. The limit as x approaches 0 from the right of the expression x to the power of x. The instructions say explore the following limits by use of your calculators, or in the case of problem 7, innovative algebra. So in this problem, we're going to use either a calculator, or I would also like to explore the possibility with you of using an Excel spreadsheet. Spreadsheets actually make the computations a little easier to do, as I hope to illustrate. Let's try to use our calculators here. I'm going to plug in a number close to 0, something like 0.1. So I'm taking that 0.1, I'm going to store this, press the store button, alpha A. I'm going to store this in memory location A, I'll hit enter, and then I'm going to take alpha A to the power of alpha A. What do we get? 0.79. It's not a huge number, not a small number. It's floating around. Let's try something closer to 0 then. 0.1 is close to 0. Let's try 0.01, wedging it even closer. Store that in memory location A and take alpha A to the power of alpha A. That gives us 0.95. That's even closer to, well, it's close to 1. It's not super close to 1, but it's close to 1. Let's try 0.001 this time. We'll store that in memory location A. We'll take variable A to the power of variable A. That gives us 0.99, even closer to 1. This is remarkably close to 1 this time. What should we do? Let's wedge something even closer to 0 in the domain from the right, so 0.0001. 3 zeros and then a 1. We'll store that, and we'll take alpha A to the power of alpha A. And you can see that now we have 0.999. That's even closer to 1. All right, let's try this again one more time. Let's plug in something like 0.000001, 5 zeros and then a 1. Let's try that. We'll store that, and alpha A to the power of alpha A, 0.99998. So this is very close to 1. Another way to do the exact same thing is like this. Let's suppose we do 0.1 in for x. And let's enter a formula. Formulas in Excel always begin with the equal sign. We're going to take that number, x, and raise it to the power of that number, x. And you can see that we got the same thing as when we typed 0.1 into the calculator and calculated 0.1 to the power of 0.1. But the nice thing about Excel is that you can change this x value to 0.01 or 0.001 or 0.000001, and you can see by getting this a little bit closer to 0, making the number smaller and smaller, closer to 0 from the right, that x to the x gets closer and closer to a value of 1. It's a little bit easier to do using Excel. You can use your calculators on these calculator problems, but if you have Excel, it might be a little bit easier. So you can see on our problem, we will declare that the limit as x goes to 0 from the right of x to the power of x is 1. We'll now look at problem number 2. X to the power 3 minus 1 all over x minus 1, and we'll take the limit as x goes to 1. Remember this, if you just plug 1 into the numerator and into the denominator, you will get 0 divided by 0. In the context of limits, 0 divided by 0 means more work. So what does this ratio tend to as x tends to 1? Let's go back to our calculation. Instead of calculating x to the power x, we'll calculate x cubed minus 1 divided by x minus 1. We want to change this x value to something close to 1 but not equal to 1. If we make it 1, we'll get division by 0. We want something close to 1 but not quite exactly 1. How about 1.01? That'll edge us off just a little bit. Notice that we get something fairly close to 3. Does it get better if we make this 0.001? That's even closer to 3. And if we make this have 4 zeros and then a 1, even better. Note that with Excel, there's a nice advantage in that you can increase the number of digits that are being shown. In fact, you can show quite a few digits using Excel. If we wedge this even closer to 1 by adding a few more zeros, in this case we have 7 zeros and then a 1, notice that we get profoundly close to 3. But in this case, we've only so far been looking at what happens as x tends to 1 from the right. The question is, what happens as x tends to 1 from the left? So I'm going to paste this formula down. And instead of using numbers to the right of 1, we're going to look at numbers to the left of 1. What if we try 0.9, just to the left of 1? To get even closer to 1, we might add a few more 9s and see what happens to this number. As you can see very plainly, it looks like it's getting closer and closer to 3, but this time approaching 3 from the other side. And the more 9s you throw in there, the closer that number gets to 3. And so we declare that the limit is 3. You can see this in another way. You can see this because we have the limit as x goes to 1, a difference of cubes. How does a difference of cubes factor? It factors as x minus 1 times x squared plus x plus 1, and that's something you might not remember. Maybe we should go through that. There's a couple of ways of seeing that this is the way you factor a difference of cubes. You can see that if the x minus 1's cancel, and then if you plug in 1, you'll have 1 squared is 1, plus 1, plus 1, and yeah, sure, you get 3. So this is another way of doing this more analytically. I want you to see this kind of numerically as well. So I want you to explore this on some kind of computing device. Calculators are nice. I think Excel works exceptionally well. How about that next problem? X goes to infinity. How do you make a number go to infinity? Well, you can't really make it go to infinity, but we'll just plug in bigger and bigger numbers. The function is 1 minus x cubed all over x squared. So let's come back here and I'll erase this stuff. I'm going to change my formula. It's going to be 1 minus x cubed divided by x squared, and we want to make the number big. Oops. So let's make this number fantastically big. Let's make it something, well, how about 1,000? What do you get? Well, looks like we're having trouble displaying this number because we've displayed too many digits. It looks like we got something like negative, pretty close to negative 1,000. What if I plug in something like with a few more zeros? How about 100,000? Looks like I'm at negative 100,000. If I displayed more digits, yeah, we display more digits, and you can see that we're almost negative 100,000. So if I plugged in positive 1 million, it looks like it might output negative 1 million. So here's my guess. The bigger the value of x that I plug in, the more this thing tends towards that value. Looks like we're tending to minus infinity. And that's what we'll write. So the next problem, we're taking the limit as x goes to infinity, but it's 1 minus x cubed divided by 3x cubed plus 2x squared minus 7. So let's go back to our spreadsheet. We're plugging in big numbers, but it's going to be equals 1 minus x cubed divided by, and I don't remember the rest of this, 3x cubed plus 2x squared minus 7. 3 times x cubed plus 2 times x squared minus 7. Now, did I remember that right? Let's go back to my page here. Yeah, minus 7. And you can see what's going on. We're getting something awfully close to negative 1/3. Oops, I want to make this black again. There. And we don't need to underline it. I got really, really big here, 100,000, and it's profoundly close to negative 1/3. What happens if I make this even bigger? 1 million, 10 million, 100 million, 1 billion. Ooh, incredibly close to negative 1/3. What do you say that our limit is equal to negative 1/3? And that we in fact expect to be the case. On problem 5, what happens in the limit as x tends to 1 from the right, 1 over x minus 1. Let's go to our spreadsheet here. We're going to 1 from the right, so I want to plug in something like 1.01. And my function is 1 divided by x minus 1. And you can see here I got 100 as an answer. Did I write that in right? 1 over x minus 1, that's right. Let's make this a little bit closer to 1 by plugging in more zeros here. What if I make this 1.0001? It got even bigger. And if I plug in more zeros, it becomes even larger. The closer this number gets to 1, the bigger this number gets. We can see then that this limit is plus infinity. What if you go to 1 from the left? That shouldn't require a lot of change here. Will be a little bit less than 1 this time. And you can see that we're getting negatives now. What happens if I get a little bit closer to 1 from the left? larger in magnitude, but still negative. And even closer to 1, even farther down the rat hole. So you can see that what we're getting here is minus infinity in this case. Now the great problem 7. What happens in the limit as delta x goes to 0 of the cube root of x plus delta x minus the cube root of x all over delta x? You can see we really should have gone back and done the work on this previous problem a little differently. On this problem number 2, we could have done this a little bit differently to demonstrate that the factorization is right. One way to see this is by long division. If you take x minus 1 and divide that into x cubed minus 1, you can see that you'd have to have x squared here. When you multiply, you'll get x cubed minus x squared, which you must subtract. That gives you a positive x squared, and then we'll have to add x. Multiplying, that's x squared minus x, which we must subtract. That gives us x. We'll carry down the minus 1. Plus 1, we'll have x minus 1, giving us a remainder of 0. There is another way to do that division synthetically. The root of the denominator is 1. The coefficients of the numerator are 1, 0, 0, and negative 1. The way you do this is you bring down this 1 right here, and then you multiply and add. Multiply and add, multiply and add, multiply and add. The last term is the remainder. The 1, and the 1 represent the coefficients of the quotient. And so you can see that this is the correct quotient with coefficients 1, 1, and 1. So now I'm going to use this factorization on problem 7. How is that going to work? We have a problem getting a numeric value here, since this should depend upon x. We'll consider these difference of cube roots as like the x minus 1 part on the previous problem. What we'll do is we'll multiply by x plus delta x to the 2/3 plus these two things multiplied together, x plus delta x to the 1/3 times x to the 1/3 plus x to the power of 2/3 divided by the exact same expression. This reduces then to the limit as delta x goes to 0. The numerator becomes the first quantity cubed. Now if I take x plus delta x to the 1/3 and cube it, it will now be to the power of 1. Minus the second term, x, to the power of 1/3 cubed, that also is to the power of 1. We have a delta x down here still, and it still times all this other stuff. In the numerator, an x and an x will cancel. that leaves only this delta x in the numerator, which can cancel now the factor of delta x in the bottom. If we cancel these out, we're left with a factor of only 1 in the numerator. So after we take the limit as delta x goes to 0, we're going to get 1 in the numerator. The question is, what about in the denominator now? Well, we'll have, as delta x goes to 0, we'll have x to the 2/3. We'll have x to the 1/3 times x to the 1/3, which is x to the 2/3. And then yet another term, x to the 2/3. That's 3 times x to the 2/3. And that is the limit. Well, I know that was pretty tricky. A lot more difficult than problem 8. Let's explore problem 8. The limit as x goes to 0 of 1 plus x to the power of 1 over x. We're going to 0. And the expression that we're evaluating is 1 plus x to the power of 1 divided by x. Now, when we have a small number like 0.1, you can see that we're not zooming off to infinity. Let's try something even closer to 1 and see if this settles on anything in particular. At 0.01, we're getting 2.7. Let's try another 0 in there. 2.71. Let's put another 0 in. 2.718. 2.7182. Let's put a couple more zeros in there. 2.71828. 1. Let's put another 0 in there. 2.7182817. It looks like it's settling down on something. The changes are only happening in very far terms now, way out there in the decimal representation. 2.71828. Now we have a problem with round-off error occurring. Adding that extra 0 in actually made things worse. What this answer should tend to is e to the power of 1. The exact value of the limit is e to the power of 1, which in Excel you write as exp of 1 with parentheses around the 1. So this is the exact value. This is the estimated value. Here we were just doing the limit from the right. Let's try to do the limit from the other side as well. I'm going to take this and copy it, put it down here. And instead of using numbers like this, we'll use, say, a negative number and see what happens. And you can see it didn't make that big of a difference. So the answer is E, which is about 2.7182818. Let's write that down on our answer sheet. We'll say this is equal to E, and that is to within some decimal approximation. Whenever I write the equals with a dot over the top, that means I'm rounding this to some decimal approximation. 818 ... So the exact value is the constant E, and that's about 2.718. Problem 9. What happens in the limit as x goes to 0 of 1 plus 1 over x to the power of x? That's similar to what we just did. Notice we're going as x goes to 0 here. But instead of 1 plus x, it's 1 plus 1 over x to the power of x. You can see what's going on here. This is a little bit different. We're having problems getting anything from the other side. Let me change this number a little bit. Numerical errors. Looks like from the right, the limit is approaching 1, but from the left, we don't have a limit at all. The function doesn't seem to be defined from the left. So it looks like the one-sided limit won't exist. If we take the limit as you go from the right, then you get 1. It looks like the limit as x goes to 0 from the left does not exist. Now, let's look at the limit as x goes to 1 from the left of the absolute value of x minus 1 over x minus 1. We're going from 1 to 1 from the left here, so I'm going to write 0.9 to begin with. This is going to be the absolute value of x minus 1 divided by x minus 1. And you can see that the value here is exactly minus 1. And if you wedge in there even a little bit closer to 1 on the left, you still get minus 1. So it seems that the value here is exactly minus 1. Notice if we did this from the other side, if we took the limit as x goes to 1 from the right, absolute value of x minus 1 over x minus 1, what would that do? That would give you positive 1 instead. No matter how many zeros you plug in there, you still get a value of exactly 1. So this would be positive 1 if we went on the other side. Okay, problem 11. The limit as x goes to 0, sine x minus x all over x cubed. We're going to 0 this time. We'll plug in something like 0.01. And let's replace all of this. The numerator is sine of x minus x divided by x cubed. Check it out. We're getting negative, a negative number, whatever it is, 0.16666. What happens if we plug some more zeros in there? What is that negative 1.6666 repetan? What is that number? So if I take 1 divided by 0.16666, a whole bunch of these, notice that's 6. In other words, this number is negative 1 divided by 6 approximately. You can see that if we have more decimal places here, we'll just have 1.666 repetan. So I would hypothesize then that the limit value is negative 1/6. So going to the paper, negative 1/6 is that value. Now, what about the next problem? Limit as x goes to 0, cosine x minus 1 plus x squared over 2 divided by x to the 4th. What's going on there? Cosine of x minus 1 plus x squared divided by 2 all over x to the power of 4. Is that right? Oops, what did I do? Oh, x. X to the power of 4. Let's see, did I remember that correctly? Yes, I did. Well, does this number look like anything in particular? Let's wedge in there a little bit closer to 0, and you can see we're getting some numerical problems. If I plug in something like one more 0, it is getting to have some numerical flakiness. This problem is going to be very, very difficult for us to do, even on Excel. We can do a little bit better job if we evaluate this using a different program. I'm going to use something called Maple, because Maple allows me to use more digits. So I'm going to increase the zoom factor here. I'm going to have, 100 digits. And I want to define x to be 0.0001. And I want to simplify sine of x, not that, cosine of x minus 1 plus x squared divided by 2 divided by x to the power 4, and that's not going to work exactly because I forgot one set of parentheses here. There. With 100 digits, you can see by adding these digits into this special program, which is called Maple, I can get even better estimates. What if I do something instead of this number? Well, what if I add more zeros? 0.041666666. What if it's accurate to the first several digits? If I plug in more zeros there, is this number close to anything in particular? Let's try the following. Let me do this way. Evaluate as a floating point number. 1 divided by 24. Do you suppose this limit value is 1 divided by 24? It looks like it gets closer and closer to that as we plug in more zeros here. We have 100 digits to play with now, so that's a lot more that you can do either with Excel or with your handheld calculators. In fact, I can increase the number of digits to pretty much whatever I'd like. I think you can see this is getting pretty close to this value of 1 divided by 24. So to make a long story short, we will be able to prove later on in this course that the value of this limit is exactly 1 divided by 24. And that's it. I hope that you had fun with today's lab, and I hope that you learned something about different technological devices that you can use to explore these limits. There's a lot more to learn in terms of the application of technology to, say, solving limits or other calculus kinds of concepts, but there are certain problems with use of these calculators. Calculator was very poor at that last problem. Excel, a little better, but not much. And Maple did a pretty good job, but it too has its limits. The theory that we develop in the future will be much better at arriving at exact values for these limits, much more satisfactory, as you will see.